Okay, so should we start? Okay, good. So as you know, in the last class, we looked at the basics of RSA crypto system, couple of machinery we covered from number theory. You know about RSA crypto system. Anyway, I have to repeat because otherwise I cannot proceed further. So I will recall the basic algorithm, and then I'm going to talk about certain complexity operations. What is the complexity of that algorithm? Then we are going to look at how to break the system, right? So basically, there are 6-step process in the RSA crypto system, and each of these process, as you know, RSA is based on factoring the integers. So the n that is used, if you can break it into prime factors, you will break the crypto system, right? So it is a difficult thing to break, to factorize. Now, there are different step-by-step algorithm. At each step, there are different algorithms that have been tried. For example, primality testing is one operation. So somebody can try random primes, right, to break the system, right? So question comes that if n is the input, how do you decide whether this is a prime or not, right? If this is the algorithm. So now, primality testing is an old problem, around 350 years old or something, and some of you know, I don't know whether you know, that it was solved. It was a difficult unsolved problem solved by Neeraj Kayal and Nitin Saxena from IIT Kanpur and Manindra Agarwal, two BTech students in a summer internship. They solved this. They provided a primality testing algorithm. So means a polynomial time algorithm in which you can determine, given an input n, is it a prime or not. It's a very small 6-page paper. Okay, so such a nice thing. So although people are using many other algorithms before that, so I'm going to talk about one or two algorithms which were there before Neeraj Kayal and Agarwal algorithm about primality testing. And similarly, we will also talk about other aspects of RSA crypto system. So basically, uh, in terms of how to attack RSA crypto system. So basically, how to individually attack algorithms have been designed, right? This much is enough for you to cover. But before that, in between, today also I have to cover some more number theory to actually understand some of the algorithms and their complexities. Okay, so let me start RSA crypto system. So you remember, you may recall, if P and Q are large primes, right, then form the product N, which is product of P and Q. Then you can find out phi of N. Phi of N, you remember, Euler-Torsion function, right? Phi of P is equal to P minus 1, phi of Q is equal to Q minus 1 if P is a prime. So it is number of integers less than N and relatively prime to N, right? By definition. This value will be what? P minus 1 into Q minus 1. So here the plain text and the cipher text coming from integer modulo N. Remember, RSA crypto system is not used for converting a large text to securing a large text, but rather, for securing the key, people use it, right? That's something very, very important. Remember, okay? If K is the pair N, P, Q, A, B, such that A into B is congruent to 1, not phi of N. For a key, then N, P, Q, A, B define encryption ek of x x raised to power b mod n and decryption dk of y is equal to y raised to power a mod n. Here x and y are in integer modulo n. Right, so okay, ignore this line. I think some line is coming. Okay, so this encryption and decryption involves this exponentiation, right? So given an integer x, so basically x is there, you raise it to power. Similarly, once you receive y, you raise it to power, right? So this is encryption decryption process. So what is the public key? N comma b, and private key P Q A. So first of all, I need to verify that encryption and decryption are the inverse processes, right? So that it makes sense when we do this. Okay. So otherwise, we don't know whether it is going to work or not. So let me check that. Okay. So let us do this calculation. So we want to check encryption and decryption are inverse processes. So what we do, proof is it's simple. Since A into B is congruent to 1 mod phi of n. That means A and B are inverse of each other, right? These exponents are inverse. This implies that AB is equal to T times phi n plus 1 for some T greater than or equal to 1. Some multiple of, right? Because of the definition. Now suppose that X is a member in Gn star. Remember Gn star? All those integers which are relatively prime to n, right, and less than n. Collection of those integers which forms a group. We saw in the last class, right? Then we can check that x raised to power b raised to power a is nothing but x raised to power t times phi of n plus 1. Everything is mod n, so I can write it down, is equal to x raised to power phi n power t times x mod n. Now x raised to power phi n is congruent to 1. That also we have done last time, right? This is congruent to 1 raised to power t x mod n equal to x mod n. Similarly, I just leave it to edit for you to check that x raised to power b raised to power a is congruent to x mod n. Right. This I leave it as an exercise for you to check this thing happens. In fact, in the discrete math class I have shown you, so I am leaving you, leave it for you so that you can just check. Okay. Okay, so now one example that we can look at it. This example also you might have done in the last discrete math class, but anyway. Suppose P is a prime 101, Q is a prime 113, and Bob chooses P and Q. N is a product 11413, product of P and Q. Then phi of n will be 100 into 112 is equal to 11200 point. Now, since 11200 is 2 raised to power 6, 5 square to 7, and integer b can be used as an exponent if and only if b is not divisible by these things. By 2, 5, and 7. So actually, in the algorithm, there was a condition: the GCD of phi n and b should be 1, and this is satisfied, right? I don't know what is happening. Okay, this GCD should be 1. So we saw how to actually compute this in the previous algorithm. I think if you remember, algorithm 6.3 was there, where we have computed the the inverse at the same time, right? So using this, you compute whether GCD is 1 or not, right? Also B inverse, you can find out B inverse at the same time. So suppose B turns out to be 3, 5, 3, 3. Okay, you can take it random. So then B inverse mod 11200 will be 6597. So Bob's, so once you know B, so this is nothing but A, right? Exponent. This is the exponent, secret exponent of Bob. Suppose plain text is 9726, then I can compute 9726 raised to power 3533 modulo 11413. This is nothing but 5761. This is our cipher text, right? This is our X, right? This is our X. So once you know that 5761 is cipher text, Bob will use this secret exponent and 5761 raised to power 6597 mod 11413. This will be 9726. Plain text you can get, right? Okay, so I think now we can talk about the implementation algorithm. What are the parameters? We call it Algo 6.4 as per your textbook. There is some problem in my writing actually, or I don't know this pen, anyway. Generate two large primes . P and Q. Of course, they are distinct signs. Second, P into Q is equal to N, and P minus 1 and Q minus 1 is equal to phi N. Choose a random B such that GCD B and phi N is 1. Fourth, compute B inverse, assign it to A, not phi N. The public key is N comma B, private key P. So the question is, what is the complexity of this algorithm? This can be done in order of log n square. I think take it from there. Sorry, this one, second step. Yeah. Okay. And then you can find out. But before doing, because this is in the modular arithmetic, all the operations are in modular arithmetic. We need to actually find out the basic complexity of modular arithmetic. So I think I'll just mention what are the complexity things. So suppose x and y are positive integers, and in the binary expansion of x, the number of bits of x is k, number of bits of y is equal to L, right? And assume that k is greater than L or equal to x plus y. एल्गोरिथम का कोर्स किया हुआ है ना, डिजाइन एंड एनालिसिस ऑफ एल्गोरिथम, डेटा स्ट्रक्चर एल्गोरिथम किया होगा पहले सेकंड ईयर में, फिर एल्गोरिथम का कोर्स किया, तो कॉम्प्लेक्सिटी ये सारी मालूम ही होगी तुमको, राइट? x plus y can be computed in order of k time. X minus y can be computed order of k time. Or division can be multiplication can be computed in order of kl time. X by y can be computed in order of L times k minus L. GCD can be computed order of k cube. In fact, there is a better algorithm in order of k square as well. I mean, I'm not saying these are the optimal ones, but these are the some estimates, right? And I think some of you already might have read Art of Computer Programming. कितने लोगों ने पढ़ ली है? नहीं पढ़ी? कॉम्पिटिटिव प्रोग्रामिंग की बुक पढ़ ली? तो एनीवे, अगर पढ़ी होती ये बुक तो देन यू नो ऑल द कॉम्प्लेक्सिटी बिजनेस एनीवे. सो now complexity in terms of in the modular arithmetic, n is a k-bit integer, and suppose M1 and M2 are two numbers less than or equal to n minus 1 means D belongs to Zn, and C be a positive integer, then complexity for M1 plus M2 mod n can be done in order of k times. Second, M1 minus M2 mod n can be done in order of k times. M1 into M2 mod n can be done in order of k square. M1 inverse mod n can be done in order of k cube. Of course, provided inverse should exist, otherwise there is no point. Fifth, M1 raised to power c exponentiation mod n can be done in order of log of c square. Okay. So this is the basic. So once you know this, you can look at the RSA crypto system and now find out for each step what is the complexity you can compute, right? Once you know the basic stuff. Anyway, so I think this algorithm, exponentiation one, that x raised to power c kind of thing, that you have to compute mod n, is actually has a better algorithm known as square and multiply algorithm. Actually, you might have seen it. I don't know. Pingla has discovered it in India, long time ago. But anyway, basically, when we want to compute x raised to power c mod of n, what is the best algorithm to compute this? X raised to power c mod n. What is the best algorithm to compute it? So C you write down as a binary expansion, and then you remember those. I think कहीं पढ़ा होगा शायद तुमने. So this can be done in order of log of n whole cube. Actually, I'm not proving all these things, but I guess I'm not leaving. These are small things, so probably you can look at it. Anyway, so first let me mention this algorithm. I'll call it as 6.4 square and multiply algorithm. Square and multiply XCN. That is going to 1 for I is equal to for I minus 1 down to 0 to z is equal to z square mod n to ci is equal to 1. Then z into x mod n and return z. Actually, here we assume that C is of the form summation Ci 2 raised for I, the binding extension, I is equal to 0 to L minus 1. Ci is either 0 or 1. It's equal to I. So I think I can give you a small exercise to see actually, work out for this algorithm, As an example, suppose n is equal to 11413, b is equal to 3533 as usual and the previous one. So the binary representation of 3533 is 11011001101. 9726 raised to power 3533 mod 11413 is equal to 5761 using this algo, 6.5. So I think I leave it as an exercise for you to just verify this. So first you write down, because I have written already the binary expansion of 3533, right? So just use square and multiply algorithm to compute this, right? You can just compute one by one what happens, right? So basically you are squaring and multiplying, right, every time. Okay. I think, so you are in, you know about Hadamard matrices, right? नवा लग रहा है ना कहीं? वैसे तो डिस्क्रीट मैथ में पढ़ाया नहीं जाता है, but actually I have covered it. So while the construction of Hadamard matrices, we talked about most beautiful thing. You remember what was that? Anyone? The most beautiful thing? What is the most beautiful thing in all literature? Mathematics, right? Mathematics is queen of all sciences. Then what? Number theory is the crown. And the gems on crown is what? Huh? You remember? And the most beautiful thing you should remember always, right? Those are known as quadratic residues, if you remember. Remember? कुछ याद नहीं होगा. कोविड में सब भूल गए, right? Anyway, so quadratic residues are very, very important, and they are used. I have shown you one application in terms of Hadamard matrix construction in your 29, I mean, in your discrete math class. Now, I'm going to cover quadratic residues, and I'll cover Legendre symbols and Jacobi symbols, and then those things are used for probability testing algorithms. So I can come up with now for the probability testing algorithm. So now you see how these things are useful. Again, I have to recall because तुम तो सब भूल गए हो, right? ये सब तो recall game ही है actually anyway. So we are going to talk about probability testing. What is probability testing? Input is an integer n. You have to give an algorithm which will tell you whether n is a prime or not, right? And the best known algorithm was discovered by Indian people, and which is by Neeraj Kayal, Nitin Saxena, and Mahinder Agrawal. And as you know, I think Mahinder is still a professor at IIT Kanpur, and recently you might have seen him on the TVs predicting about COVID-19. अब क्या होगा, कितने cases आएंगे? You remember? That was Mahinder Agrawal. If you are good in mathematics, you can do anything. So next is, I think, Neeraj. One of them is in Microsoft. Another one is a professor at IIT Kanpur. I think so. One of those students. So after this, after the BTech from IIT Kanpur, they finished PhD at IIT Kanpur only. Okay, and one went to Princeton, another one went to Microsoft. Anyway, so this is something. So I'm going to talk about quadratic residues. Example से शुरुआत करते हैं, right? Let us start with an example so that you can recall. P is equal to 11. Prime. P is a prime. 11. What is 1 square? 1. 2 square? 4. Yeah, I don't know. Maybe somebody should teach me how to write here. See all these problems. 3 square is 9. Modulo 11. Everything is modulo 11, right? 4 square is 5. 5 square is 3. Same thing as 6 square. Same thing as 7 square. same thing as 8 square, same thing as 9 square, same thing as 10 square. Do you agree? So 11 से जितने छोटे नंबर थे 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I just squared them and reduced it modulo 11. So I got certain set of numbers, right? What are those numbers? 1, 4, 1, 3, 4, 5, 9, and so I can write it down. Quadratic residue. And जो बच गए quadratic non-residues. ठीक है ना? So can you find out for p is equal to 5? Prime अगर हमारा 5 है तो what are quadratic residues? 1, 4 and 2 and 3 are quadratic non-residues. This is all. बाकी उसमें definition लिखेंगे लंबी चौड़ी, you know, all that. Examples are better, but anyway. But you know, so the question is, if n is an integer, I give it to you. Of course, prime p is given to you. That p is an odd prime, and n is an integer given to you. Or a is, sorry, n नहीं use होता है notation में, a use होता है. If a is an integer given to you, can you give a good algorithm to decide whether a is a quadratic residue or quadratic non-residue? कैसे सोचोगे? A is given to you. P is fixed. Suppose P is fixed, odd prime, and I give you an integer A. You tell whether it is quadratic residue or quadratic non-residue. Okay. So there are some nice characterizations. I can just mention one of them, which is, you know, good enough for you to understand. By the way, if you want, I can write about the definition. Forget it. Your problem. Okay. Question is, so given is an odd prime P and an integer A. Question is A quadratic residue, not P? So there is a theorem known as Euler's criteria. P is a odd prime. A is a quadratic residue, not P, if and only if A raised to power P minus 1 by 2 is congruent to 1. By the way, how do you think about these things, you know? So you saw the example, you understood the definition, and somebody asks you to discover a theorem. How will you discover a theorem? Anybody written a paper, research paper, till third year? No? कोई पेपर लिखा है मशीन लर्निंग में लिखा हुआ कि कभी कॉम्पिटिटिव प्रोग्रामिंग ही चल रही है अभी भी? तो basically, you see, in mathematics, whenever what you do, if you have to discover a theorem, you generate a lot of data, at least in C, observe the pattern. Okay, once you observe the pattern, make a conjecture and then try to prove it. So somebody might have observed this conjecture. If this happens, you know, by the way, you can use machine learning to find out such kind of theorems. That's a new branch. Machine learning can be applied to mathematical data to discover the theorem. That is also a possibility. If you are a fan about machine learning thing, right? By the way. So otherwise people, they analyze, observe. The best way to discover mathematics is to observe the data, right? ऐसे देखते रहो शून्य में, then you will observe some nice thing, right? Anyway, so let me give you a proof first. Once you discover the fact, then you can prove it. Suppose am I right? It is given that A is a quadratic residue modulo P. That means A is something y square mod P. You just saw the example, right? For some y, which is okay. Because in all quadratic residues, square was there, right? We are doing that same thing. Now, if P is a prime, then you know that A raised to power P minus 1 is congruent to 1 mod P. I'm very tired with this. Sometime it will write a line, sometime it will not write a line, but anyway. A raised to power P minus 1 is congruent to 1 mod P. This you know, right? If you know this fact, then you can consider A raised to power P minus 1 by 2 and see what happens, right? This implies that A raised to power P minus 1 by 2 congruent to y square raised to power P minus 1 by 2 equal to y raised to power P minus 1 equal to 1 mod P. So we found the solution, right? I mean, one way it is proved. When A is a quadratic residue mod P, then we know that A raised to power P minus 1 by 2 is congruent to 1 mod P. Reverse can be proved easily. अरे तुम लोग तो बहुत दिनों बाद मिले हो, मैंने तो टी प्रॉब्लम देना बंद कर दिया था ऑनलाइन, राइट? Okay, reverse. At least you should think about it, right? How to prove the reverse. चाय तो पीने लगे होगे ना आजकल, गन्ने का रस पी रहे हो तो. Okay, so I think एक साइड प्रूव कर लिया, दूसरा साइड अपने आप करने की कोशिश करो चाय पीते हुए, राइट? एनीवे, एक छोटा सा डेफिनेशन और दूंगा एंड देन वी विल क्लोज टुडे, राइट? ज्यादा गर्मी में पढ़ाई बढ़ाई भी नहीं होती है, राइट? तो एनीवे, Legendre symbol P is a odd prime. This is 0 if A is a multiple of P. 1 if A is a quadratic residue mod P. And minus 1 if A is a quadratic non-residue mod P. This is known as Legendre symbol. This is quite useful in a lot of algorithms, number theoretical algorithms and so on. Then we have a theorem. If P is a odd prime, Then this thing is same thing as this. So this is very easy to prove. Again, I will just verbally say a few words. First, if A is a multiple of P, then what will happen? This quantity is 0 anyway, which is same thing as this by definition. If A is a multiple of P, right? So both sides are same. When A is a quadratic residue, then this quantity is 1, you saw, and this is also 1, right? -1 का ट्राई के लिए छोड़ देते हैं, ठीक है? I mean, just few words, right? Not very difficult, anything, anything. I'm not saying anything which is very difficult, Last thing is Jacobi symbol. N is a odd positive integer, and suppose n has the following factorization: I is equal to 1 to k. A is an integer, then is equal to Jacobi symbol is defined as, so this is a Legendre symbol because it is defined for primes. Okay, primes, and this is for any integer n. So I will just do small. I will just do one small example. Six two seven eight 9975. Find out this value. Since 9975 can be written as 3 into 5 square into 7 into 19. This implies that 6278 divided by 9975 is equal to 6278 divided by 3 from first factor into 6278 divided by 5 square into 6278 divided by 7 into 6278 divided by 19. For all prime factors, we have got this. This can be simplified: 2 by 3, 3 by 5 square, 6 by 7, 8 by 19. So by definition, this is -1 whole square, -1 depending upon quadratic residue, quadratic non-residue business. For each prime, whole thing is -1. So this is how you can do. So I think it's not very difficult. So you can. So I talked about quadratic residues. I talked about Jacobi symbol. I talked about Legendre symbol. Right. That's all. So in Legendre symbol, the denominator is prime number. Here it is, anything. So you just write down the factorization and then open it and then do this. There are many interesting results. If at all you do, I don't know whether you will do. Probably I will be posting some. I taught a course on computational number theory, where we discuss these things in details. Okay, all the algorithms. I'll upload all the videos. It's not there. Yeah, I hope you will watch if you have interest at all, other than competitive programming, right? But anyway, so that's all. I think morning lecture will be very good. Actually, 8:30. Na? Afternoon mein neend aati hai, right? So it's good. So we'll see you on Thursday morning. And I think we'll be look at slowly towards, we'll go towards the attack. I'll look at some algorithms first for the primality testing. Okay, the basic algorithms, so that you understand the basic things. Because this is of course, there are many known algorithms, but anyway, I'm not going to look at all of them. whatever is given in your textbook, I'm just following that so that you have some reading material to do that. Okay. Okay, that's all for today. So thank you. Looks nice. We can meet on Thursday, 8:30, same room, right? And if you have any doubts about your projects, please you can come and ask me. Okay, in my office.